This one's easy. So gas has no definite volume and no definite shape. It just fills and assumes its container's shape. Gas creates pressure. It gets excited when you heat it. It mixes in any proportions. And it's way less dense than water, so instead of grams per milliliter like we do with liquids, we say grams per liter when we're talking about gas, because there's a lot fewer grams of a gas per liter. All right, here's the test question. What's in our atmosphere? Our atmosphere is like a 50 kilometer, 1 hour, straight up, thick layer of gas. What is 78% of it?
Nitrogen.
Nitrogen. What is 21% of it?
O2.
Yep, oxygen, good. 0.9%.
Argon.
Argon, 0.03%.
CO2.
CO2, 0.002%.
Methane.
Methane, farts, and 0.00005%.
Hydrogen.
Hydrogen, good. There is a pressure due to the gravitational pull of the atmosphere. It's atmospheric pressure. So we'll say force to surface area, P equals F over A. And that is the gravitational pressure. P equals F over A. Gravitational force of the air, the gases towards the earth. That is called atmospheric pressure. And when we're doing any kind of chemical reaction, we are assuming, unless otherwise told, that I have a normal pressure going on. So PATM is my assumable pressure of any gaseous chemical reaction, unless otherwise stated. What tool is it measured with? Pressure? Atmospheric pressure?
Barometer.
A barometer. What element is used?
Mercury.
Mercury in that barometer. So I can have 1 atmosphere, ATM. I can have millimeters mercury, or I can have torr as units of pressure. But unfortunately, what the SI unit is Pascal.
Pascal.
PA. So the SI unit for pressure is the Pascal, PA. How many, here, let's just do this. My barometer at sea level, right? At sea level, my barometer says 760 millimeters of mercury. So we're gonna call that 1 atmosphere. But we're also gonna call that 760 torr. So if you ever see that. But we're also gonna call that 101,325 Pascal, which is the SI unit. Not the one we use, but it is the SI unit. And then what do we do to that because it's so big? What do we use the kilopascal now, right? So bummer. So we don't like that Pascal guy. We definitely like millimeters mercury better or torr better. But again, the pressure from the atmosphere at sea level pushes the mercury in that tub down, which sucks it up the straw to about 760 millimeters of mercury. 760 millimeters up that straw at sea level. That makes sense. I like that because it's pretty. All right, who was pressure versus volume?
Boil.
Boyle. And what's the relationship called? Inversely proportional. Give me an example of Boyle's law. I used balloons. You can use anything you want.
Balloons.
Balloons are easier, aren't they? Because they're stretchable. So what happens with Boyle's law? Give me an example.
If it goes up, the balloon gets bigger. If it goes down, the balloon gets smaller. Underwater.
So underwater, so my example was you drag a balloon down into the sea, the pressure is going to increase, so the volume is going to decrease, and my balloon is going to get smaller undersea. What if I said I took it up a mountain? I took a balloon to Denver. What's going to have happened?
Pressure, volume's going to go up.
Yeah. I'm decreasing the pressure. So the air is thin in Denver when I'm up in the mountains, right? So I take that balloon up, it's going to get bigger. Okay? It's going to be free to expand. What did Charles say? What two things did he compare?
Volume and temperature.
Volume and temperature.
Directly proportional.
Directly proportional. So Boyle's was inverse. Charles is direct. So what's going to happen if my balloon heats up? It's going to expand. I know that. I bought balloons before for a birthday party, took them out on a cold day, and then they look like they don't have any air in them. They're smaller and kind of wobbly, right? Then I get them inside the warm house and psh, they're big again. What am I assuming then? If I'm comparing volume and temperature, then what am I assuming? Constant pressure, which is my 1 atmosphere of pressure. I know we just did these. Volume and quantity is who? Avocado. I'm assuming pressure and temperature are constant, and I'm gonna say my volume of my balloon is gonna increase with the number of moles I put in it. So if I put a little more helium in it, then it's going to expand. The volume is gonna get bigger. Okay? So volume is directly proportionate to number of moles in. What did Amunton say?
Pressure and temp.
Pressure and temp.
Directly proportional.
They're directly proportional. So what I'm saying is if I heat this balloon,
The pressure's gonna go up.
the pressure is gonna increase. They're gonna bounce off the walls of that balloon with more force. They're adding pressure, right? And then what was my ideal gas law in a nutshell? PV nRT, which is like pressure, volume, number of moles,
Universal
constant,
temp.
ideal gas constant, and then temperature. And what was my ideal gas constant? I'll give it to you, but I do want it on your paper.
Which one?
It's
Which one
the
was it?
R.
The 0.0206 or 8.
So, excuse me guys. 0.08206 liters times atmospheres over moles times Kelvin. The reason why you want to know liters times atmosphere over mole times Kelvin is because you need to know if, in this ideal constant, what you need to convert, if anything. So pressure for ideal gas is in atmospheres. Volume is in liters. This is moles. This is 0.08, what is it? 0.08206.
Yeah.
And this is, oh gosh darn it. Liters, oh gosh. Moles. Kelvin, which means that this is in Kelvin. Okay. But knowing the units is half the battle, right? Because if it says milliliters, you're never gonna get the right answer if you keep it in milliliters. So let's do one. And it was, what volume of oxygen is needed to burn 1 kilogram or 2 pounds of charcoal at 1 atmosphere pressure on a summer day that's 25 degrees Celsius. Remember this guy? What volume of O2 is needed to burn 1 kilogram of charcoal at sea level on a 25 degrees Celsius summer day. So I gotta do some stuff. The first thing I need to know is, how do I do this? What does this chemical reaction look like? What kind of chemical reaction am I doing? I got oxygen and I'm burning.
Combustion.
Combustion. Step 1, this is combustion. So I know that I have a solid form of carbon and charcoal, and anytime I have a combustion, then it's whatever my beginning combustible is plus O2, and what does it give off in combustion reaction?
H2O and CO2.
Ooh, CO2 and heat. In this example, because I'm not starting with any hydrogen. But yes, you're right. All right, well, do I need to balance this in any way? It's balanced.
No.
Okay, good. So we know we're doing 1 for 1 on moles here. okay? Now, what do I start with? 1 kilogram of carbon. Well, I know I don't want kilogram. What do I want? Grams per mole, right? So 1 kilogram is 10 to the third grams. That is the, excuse me, silly little pico, the tens, right? Chart that you have to have on your cheat sheet. It's like from the first chapter. If you don't have the tens chart that says a picometer or a whatever is like 10 to the 19th, then you know, you won't be able to do it. 1 mole of carbon is 12.01 grams of carbon. I know that from right there on my molecular mass. So from this, I can get 83.3 moles. Now, I don't want moles of carbon. What do I want moles of? Oxygen. What I'm looking for is how much oxygen is needed. So if I want to know how much oxygen I have, then I have to say, okay, how many moles per carbon equals moles of oxygen? Luckily, because this is already balanced, we know it's 1 mole of carbon equals 1 mole of oxygen. Even though there's 2 oxygen, it has to be, moles has to be the number up here, right? And there's no numbers up there, so it's 1 to 1. Does that make sense to everybody?
Yeah.
So I can also say that that's how many moles of oxygen I have. That's what I need. If I'm gonna solve my ideal gas law for volume, I have to take volume out of the equation and do V equals, now, what did I say about pressure and volume?
Inverse.
They're inverse, so this always, if I pull out P, V has to be down there. If I pull out V, P has to be down there. Okay? So I have to inverse the pressure, but the rest of them are fine to hang out with volume. Be multiplied. Does that make sense, everybody? Okay. Now I just plug it in. This was 83.3 moles. This was my constant, which was 0.08206. I have to convert 25 degrees Celsius to Kelvin, but all I have to do here is add what? If I want this to be Kelvin,
273.15.
273. So what do I get there? 298. Cool? And then my pressure is 1 atmosphere. So basically all I'm doing is multiplying these 3 items to get my volume. So V equals 2.04 times 10 to the third liters of oxygen, but 10 to the third is pretty easy, and I want us to kind of see $2,000 liters of oxygen, approximately. Have you guys ever been around a big fire? Can you feel, like, even a big bonfire, if you're standing next to like a burn pile, you know, we're from Kansas, people have burn parties here, right?
Yeah.
So they'll pile up the trees and debris and other stuff, sometimes garbage, because a lot of these people just, they don't have trash collectors, they either take it themselves or So they pile stuff up, and it's just this huge mound, and then they have a weenie roast, and everybody brings a side dish, and wears their cowboy boots, and they put music on, and they burn it, right? And we all dance around the fire. Do you feel the draft?
Yeah.
It's a skirt blowing draft towards that fire. What is it? It's oxygen. Why would it draft into the fire?
Keep it going.
To keep it going. So what I'm doing is I'm burning this fire. I'm making CO2, and CO2 is burgering off to go into the atmosphere and become bad things, right? Like carbonic acid, right? But the CO2 is lifting up. Well, molecules, especially gaseous molecules, don't want to be around each other. So basically what this fire is doing is making a vacuum, a void of oxygen. And the oxygen's like, hey guys, let's spread out. There's a room being made right here. So I'm going to go into it, right? So they're getting away from each other right here and going into the part where there's not very many oxygen. And so what's happening is now this fire is making it void of oxygen right here. So oxygen's literally running and rushing through and swinging your skirt as it goes by and going into the fire.
Is that 'cause it's like carbon?
Yeah. I mean, because the fire ends up using that oxygen and making CO2, it's not going to be back and forth.
Right.
But the
But
rush
more
in,
than
right.
things.
Right, so it's making CO2 and CO2 is bunkering off, and so it doesn't unreact. The CO2 never goes back to just oxygen and carbon, but with burning this charcoal, I have this draft. So what happens in a building that's burning? See, I shut this door and this room is burning.
We run out of oxygen.
It's running out of oxygen. Eventually it would die, it would kill itself, right? So I dated a firefighter for a while, right? And years ago, but he would be like, every time we'd leave for a vacation, because that's what I do, he would shut all the doors on the house. I'm like, what are you doing? He's like, if a fire starts, it could put itself out, right? If it has no source. So what happens if you're like, run into your house, oh my God, I gotta get my pictures. And you open this door. Oxygen rushes in. So at first, it's this, and then it fuels the fire. So now, the fire gets bigger, right? So that's called a backdraft. When you open a seal, or at least a limiting wall or door or reagent, you open it, the oxygen rushes in, it feeds your fire that was starting to smother, and then the flames rush out, right? So that's what our backdraft is, and that's all explained in, you're taking 2,000 liters right around your little grill of oxygen from the air. If it's open, sweet. That works out all right. If it's in some kind of closed situation, it's a problem, right? Either a problem of not having enough oxygen to make it happen, or ending up, somebody opens the door then, like you're inside the barn trying to burn, somebody opens the door and then, right? Big fire. Okay, that's my gas reactions. So, test essay. You'll have to do a reaction like this, and then you'll have to answer a question that goes something like, explain backdraft in terms of combustion and oxygen usage. I say oxygen consumption. Okay? So if you want to take a minute to write that answer down, you're welcome to do that.